Welcome to the Deep Dive, the only place where 4 billion years of planetary history feels like a thrilling afternoon conversation. Today, we are undertaking what might be, well, the most fundamental geological history deep dive possible. We're charting the shift that transformed Earth from a really hostile anoxic world into the blue marble we know today.
Yeah, we're going way back, Hadean, Archean eons, focusing on the Great Oxidation Event, the GOE. And we often frame this as just, oh, life started making oxygen. But that really misses the planetary context, the bigger picture.
Yeah.
Our mission today really is to show you that the GOE was fundamentally a geological event. It was a threshold crossing that needed Earth's crust, its water cycle, its volcanoes. All that had to mature first. Only then could oxygen, which was basically life's waste product, finally start to build up. That's such a powerful way to reframe it. So we're looking at three deeply connected systems, right? Okay. The hydrosphere, where the water came from, crustal dynamics, how the continents actually moved or didn't move, and atmospheric chemistry, their whole greenhouse thing.
Exactly. They're coupled, intensely coupled.
If any one of those steps had failed, or even just lagged behind too much, well, we wouldn't be here talking about it. Because complex life, our kind of life, needs oxygen.
Yeah.
And it needs a stable planet.
Absolutely. And we have to start, I think, with the biggest conceptual hurdle first. It's this revision of the early Earth timeline. You hear Hadean, and most people immediately picture this, prolonged, fiery chaos like Dante's Inferno, but planetary scale.
Right. Hellfire and brimstone, a molten mess.
But the geological sources, the geochemistry, they actually reveal something stunningly different, a contradiction, really. The Hadean seems to have been a period of astonishingly rapid planetary organization.
Okay, I admit I found that detail genuinely shocking when reading the materials. It wasn't a slow, gradual build. It was like, bang, an accelerated start.
That's it. We're talking about evidence for liquid water and stable continental material, not necessarily continents yet, but the stuff they're made of being present. Well, the zircon evidence constrains it to about 4.4 billion years ago. Not 4 billion, 4.4.
So almost right after the planet itself formed. That initial organization was practically instantaneous, geologically speaking.
Pretty much.
Okay, let's unpack that speed then, starting right at the beginning.
Yeah.
Earth forming, accreting around 4.57 billion years ago. And then that massive moon-forming impact, the one that basically reset the clock and created this planet-spanning magma ocean. That sounds like maximum chaos to me.
Oh, it was chaos, definitely. But a remarkably brief chaos. The sources really emphasize the speed of the cooling. That initial magma ocean covering the entire planet, it didn't stay molten for millions and millions of years. The estimates are it solidified or at least crusted over within maybe 5 million years.
5 million years. On a geological time scale, that's nothing. That's immediate.
Functionally immediate, yeah. From a molten ball to something with a solid or solidifying surface capable of, supporting some kind of early crust.
And why was that rapid solidification so critical for what happened next? The outgassing.
Because as that mantle rock, the silicate material, solidified, it basically squeezed out the volatile elements. Gases like water vapor, CO2, nitrogen, stuff that was dissolved in the magma. It was forced out. It erupted massively and immediately through intense volcanism. That's what established Earth's very first primordial atmosphere.
And what kind of surface environment did that create, that initial rapid outgassing?
Truly alien. Hostile doesn't even quite cover it. Think thick, heavy, and incredibly hot. The atmosphere is loaded with carbon dioxide, CO2, tons of water vapor, hydrogen too. And crucially, the sources estimate initial surface conditions were maybe around 230 degrees Celsius.
230 C.
Yeah, and the atmospheric pressure, probably more than 27 times what it is today.
Wow, okay. 27 standard atmospheres. That high pressure, that's key, isn't it? It would let water stay liquid well above its normal boiling point.
Precisely. Even at 230 C, water could exist as a liquid on the surface under that kind of pressure, which gives us a mechanism to actually hold on to the water that was arriving or being outgassed. And this leads us right into that critical revision we mentioned, the early timing and the sort of dual origin of Earth's oceans. How do we get from 230 degrees C to having actual liquid oceans?
And so early, too.
The smoking gun, or maybe the hardest evidence we have, comes from these tiny, incredibly resistant minerals, detrital zircon grains, particularly the ones found in the Jack Hills of Western Australia.
Ah,
These things are like mineral time capsules. They're super robust. They survive billions of years of geological recycling.
And scientists have dated some of these Jack Hills zircons back to 4.4 billion years ago.
That's right, 4.4 Gaia. And they aren't just dates. These zircons act like tiny planetary thermometers and even hygrometers in a way.
How do they constrain the conditions so precisely? What's inside them?
It's all about the trace elements and isotopes locked into the crystal structure when they formed. For example, you can analyze the amount of titanium trapped inside. Titanium incorporation is very sensitive to temperature. So based on the Ti content and also oxygen isotope ratios in these 4.4 billion-year-old zircons, researchers can model the environment they crystallized in, and the models point strongly towards formation in the presence of liquid water, interacting with some kind of stable, probably silica-rich crustal material.
Wait a minute. If there was liquid water, then the surface temperatures must have already dropped significantly. Maybe not everywhere, but at least locally. Below 100 C, or maybe a bit higher if the pressure was still up.
Exactly. It means the planet must have cooled down enough, probably quite rapidly through condensation of that massive water vapor cloud, maybe some early feedback loops, cool enough to sustain pools or maybe even shallow seas of liquid water, long before the formal end of the Hadean era.
It just completely upends that traditional picture of a totally molten, sterile Hadean.
It really does. The water cycle was likely established incredibly early.
Okay, so if the water was there by 4.4 gig, we need to know where it came from and why it accumulated so incredibly fast. The sources talk about a dual origin, external delivery and internal expulsion. Let's start with the external bit. What's the isotopic fingerprint telling us?
The primary source seems to be extraterrestrial, yes. If you look at the deuterium to hydrogen ratio, the DH ratio in today's ocean water, it acts like a chemical signature. And that signature is a very close match to the DH ratios found in a specific class of meteorites, carbonaceous chondrite.
Asteroids, basically, volatile-rich asteroids left over from the solar system's formation.
That's the idea. They likely deliver a significant fraction of Earth's water inventory, probably during the later stages of accretion.
But the timing.
Yeah.
4.4 gig that suggests the planet didn't just sit there passively waiting for asteroid deliveries over hundreds of millions of years. It had to be actively involved to get oceans so fast.
Absolutely. That's where the internal expulsion mechanism becomes crucial for the speed. While the water molecules might have largely originated from space, a lot of that volatile material probably got incorporated into the mantle rock as the magma ocean solidified. It was dissolved in the rock.
Trapped inside.
Exactly. So to form a global ocean, or at least very large bodies of water, within the first, say, 100 or 200 million years, you needed truly massive, unprecedented rates of volcanism during the Hadean to essentially sweat out that trapped water rapidly.
And you mentioned the contrast earlier. If Earth relied only on today's volcanic degassing rates,
Oh, it would take forever. Something like 12 billion years to generate the amount of water in our current oceans. Longer than the age of the universe.
so the math just doesn't work without that early, intense volcanic outgassing.
Not at all. The sheer volume demands an outgassing rate orders of magnitude higher in the Hadean. The implication is that the planet's intense internal heat didn't just drive rapid crust formation, it also provided the volcanic plumbing needed to furiously degas water from the mantle. That water then condensed, pooled, and maybe formed a kind of superocean covering much of the early Earth. It was just an incredibly high-flex system that got the hydrosphere online almost immediately.
Okay, so we've got water established incredibly early. Now we need to understand the crust it was interacting with. And this moves us into what you flagged as one of the most contentious areas in geology. What was the geodynamic regime? How did the early Earth's crust actually behave? We're so used to modern plate tectonics, but that intense Hadean heat, that also presented a huge challenge to that system, right?
A massive challenge. Yeah, this is where the debates really heat up, literally. Early Earth's mantle was significantly hotter, maybe hundreds of degrees Celsius hotter than today. That means mantle convection was far more vigorous. And this elevated heat flow is precisely why geologists argue about whether modern-style plate tectonics, what we call a mobile lid regime, could have even operated back then.
Why does higher temperature make stable subduction so difficult? What's the mechanism?
Well, modern subduction relies on the lithosphere, that rigid outer layer of crust and upper mantle being cool enough and therefore dense enough to sink deep into the mantle under its own weight. It's a process called slab pull.
gravity basically pulling the plate down.
Exactly. But on the early Earth, the lithosphere would have been much warmer and therefore less dense, more buoyant. Like trying to sink a warm piece of wood compared to a cold, dense rock. A warmer, more buoyant lithosphere resists sinking. That makes the stable, continuous subduction needed for global, mobile lid tectonics really, really difficult, maybe even impossible to sustain globally.
Okay, so if we didn't have the kind of plate tectonics we see today, the full mobile lid system, what was there instead? This is where the idea of a lid-to-plate transition comes in, starting with something like a stagnant or maybe a sluggish lid.
That's the prevailing hypothesis, yes. Under a true stagnant lid, the entire surface lithosphere is basically one rigid, unmoving piece, like Venus seems to be today. In that scenario, crust gets generated vertically. You have massive mantle plumes punching up from below, erupting lava, building crust from the bottom up, but no real lateral movement or recycling.
And a sluggish lid would be somewhere in between, maybe some limited movement.
Sort of, yeah. Maybe episodic subduction or localized deformation, but not the globally interconnected system we have now. Modern tectonics, with its continents drifting, plates colliding, and extensive recycling. That represents an evolution from that initial, more rigid or sluggish state.
And the timing of that switch,
Yeah.
the uncertainty is just enormous, isn't it? I saw estimates in the sources that span billions of years.
The range is frankly huge. Some studies argue for hints of mobile tectonics almost right away, back in the Hadean or Eoarchean. Others suggest a stable global system didn't really lock in until maybe the Neo-Proterozoic, like less than a billion years ago. It's incredibly difficult to pin down, partly because the rock record from the Hadean is virtually gone, and any early tectonic evidence gets easily overwritten or destroyed by later geological events. We're hunting for chemical fingerprints left behind in the toughest, most resilient minerals, like those zircons again.
Right, let's focus on those chemical fingerprints then, because they give us the first really solid evidence that even if full tectonics wasn't happening, rapid crustal establishment certainly was. There's fascinating geochemical evidence confirming rapid chemical separation between the crust and the mantle, right?
Yes, absolutely. We look mainly at isotopic systems. These involve trace elements that behave differently when rock melts and separates or differentiates. A key system is lutetium-hafnium, or LuHF. Lutetium tends to stay behind in the mantle residue during melting, while hafnium prefers to go into the melt that eventually forms continental crust.
Ah, okay. So by measuring the ratio, the parent lutetium isotope to the daughter hafnium isotope, it decays into over time.
Yeah.
You can figure out when that chemical split happened, when the crust first separated from the mantle.
Precisely. It's a powerful geochronometer for crust-mantle differentiation. And the LuHF data from the oldest rocks and zircons confirms that this fundamental chemical separation started extremely early, maybe as early as 4.5 billion years ago, essentially right after the moon-forming impact. And there's complementary evidence, too, from neodymium isotopes. Specifically, variations in mu-142 neodymium in Eoarchean rocks suggest that a depleted mantle reservoir, a part of the mantle that had already had melted extracted from it, had formed by about 4.4 billion years ago.
There's that number again, 4.4 gat. It keeps popping up. So it wasn't just liquid water by then. The fundamental chemical layering of the planet, crust distinct from mantle, was also established.
It looks that way. The planet seems to have set up its three key systems, water, crust, atmosphere, almost simultaneously within its first couple hundred million years. The pace is just remarkable.
The pace of organization, yeah. And these systems started interacting immediately.
Seems so. For instance, oxygen isotope studies in some very old Archean gneisses, these metamorphosed rocks. Their compositions suggest the original rocks, their precursors, had interacted with large amounts of surface water, probably through high-temperature hydrothermal alteration like underwater volcanic vents. So the newly forming crust was definitely talking chemically to the early ocean.
Okay, this early interaction, this evidence for water influencing rock chemistry, it starts to challenge that simple stagnant-lid model, doesn't it? This leads towards what the sources called the hybrid tectonics conclusion. If the lid was supposed to be totally stagnant, how did scientists find evidence that looks like mobility in rocks nearly 4 billion years old?
Again, the key is often in those ancient zircons. Specifically, work done on zircons from places like the Acasta Gneiss complex in Canada and the Sagla Hebron complex in Greenland. These contain some of the oldest known terrestrial materials, dating back close to 3.9 billion years ago, maybe even older.
And scientists are looking at trace elements within those zircons as proxies, like little clues about the tectonic environment where they formed.
Exactly. They use combinations of trace elements like uranium, niobium, scandium, ytterbium, U-NBS-CYB ratios, for instance. The thing is, in modern geology, certain signatures in these trace elements are strongly associated with magmas formed by hydrous melting. That means melting rock in the presence of water.
And hydrosmelting. That's the classic fingerprint of subduction zones today, right? Where water trapped in the downgoing oceanic plate gets released at depth and triggers melting in the overlying mantle wedge.
That's the textbook definition of arc magmatism, driven by mobile lid tectonics, yes. And the crucial, really exciting finding was that these ancient Eorchian zircons from 3.9 billion years ago, they show these trace element signatures consistent with hydrous melting.
Suggesting water was getting deep into the crust or upper mantle, forcing melting, even back then.
That's the implication. It strongly suggests processes akin to subduction, or at least involving significant water infiltration deep down were happening.
So why not just declare victory for early plate tectonics then? If we see subduction-like signatures at 3.9 geo, why is it still called hybrid?
Because of the hybrid part. It's because these mobile lid-like signatures weren't uniform. They sort of coexisted with different isotopic signatures found in other ancient terrains from the same broad time period. For example, you find zircons with these hydrous melting trace elements, but maybe their hafnium or oxygen isotope ratios are quite different from similar aged zircons found elsewhere. If you had global modern-style plate tectonics fully operating, you'd expect the constant mixing and recycling to produce a much more uniform, globally consistent chemical signature in the magmas being produced.
Okay, so the geochemical diversity is the key. The lack of uniformity suggests it wasn't a single global system yet. We had pockets of different activity.
Precisely. It points towards a diversity of coeval tectonic regimes. You didn't have one single mode operating everywhere. Instead, the early Earth was likely running a kind of messy experimental phase. You probably still had stagnant-lid type processes, like plume volcanism, dominant in some areas. But alongside that, you had localized zones where mobile lid or arc-like processes were starting to kick in, maybe triggered by mantle plumes interacting with the lid or by regional stresses. It wasn't global, but it was happening in places.
And this messy hybrid phase might have been essential because it was forcing water deep down, starting to create that chemically differentiated continental crust needed for later stability.
That seems to be the critical outcome. It started the process of making true continents, even if the engine wasn't fully modern yet.
All right, so we've established liquid water surprisingly early, and a crust that was dynamically evolving, even if messily, by the Eorchian, maybe 3.9 billion years ago. But for liquid water to exist, you need enough energy to keep it from freezing, and that brings us face to face with a huge thermodynamic problem. The faint young sun paradox. If the sun was much dimmer back then, how on earth did the planet avoid becoming a global snowball?
Yeah, the FYSP is a classic, and it's a tough one. The astrophysics is pretty clear. Stars like our sun increased their luminosity over billions of years. Back in the Hadean and Archean, the sun was probably only putting out about 70%, maybe 75% of its current energy.
50%.
Yeah, and if you plug that low solar output into a basic climate model using today's atmospheric composition, Earth freezes. Solid. For maybe the first 2 billion years of its history.
But all the geological evidence we just discussed, the 4.4 gas zircons implying liquid water, the ancient sediments formed in water flatly contradicts that. It screams warm and wet, not frozen solid.
Exactly. The geology demands liquid water. The physics seems to forbid it. That's the paradox.
So simple physics requires some kind of massive compensation in the atmosphere. The only way out is a much stronger greenhouse effect, right?
That's the consensus solution, yes. We needed incredibly high concentrations of greenhouse gases to trap what little heat the faint sun was providing.
And the engine for that had to be the intense volcanism we already talked about.
Correct. The early Earth's hyperactive volcanism, driven by that higher internal heat, was continuously pumping enormous volumes of greenhouse gases, primarily CO2 and probably nitrogen too, into the atmosphere. This created a thick, insulating greenhouse blanket that compensated for the weak sunlight.
Can we put some numbers on that? How much CO2 are we talking about?
The climate modeling suggests that to keep average surface temperatures consistently above freezing, CO2 concentrations needed to be somewhere between 100 and perhaps even 1,000 times the present atmospheric level, the PAL.
1,000 times.
Potentially, yeah. That translates to a partial pressure of CO2 of roughly zero point zero 0.03 bar up to maybe zero point 0.3 bar, compared to today's 0.00004 bar. A huge difference. This massive carbon dioxide shield seems to be the primary mechanism that resolves the paradox. It kept the planet warm enough for liquid water.
Okay, but here's the thing. Earth today has natural thermostats, right? If CO2 spikes, things like silicate weathering ramp up and draw it back down over geological time. Why didn't that happen back then? Why did this huge CO2 reservoir persist for, well, billions of years through the Archean? Why were the sinks restricted?
The restriction of the sinks. That is absolutely key to understanding Archean climate stability. You're right, the main long-term CO2 sink is silicate weathering. Atmospheric CO2 dissolves in rainwater, forms carbonic acid, reacts with silicate rocks on land. The reaction products get washed into the oceans, and eventually the carbon gets locked up in carbonate rocks, like limestone. It's Earth's main geological thermostat.
But that thermostat was turned way down in the Archean.
Critically dampened, yes. And the hypothesis connects directly back to the tectonics and high heat flow we discussed.
Ah, okay. How so?
Because of that higher mantle heat flow, the early Earth's lithosphere was generally hotter, probably thinner, and definitely more buoyant. This likely made it very difficult for the planet to build and sustain large, high-standing, stable continental land masses like we have today. The overall topography was probably much more subdued, lower elevations, maybe more like volcanic islands and submerged platforms rather than vast high continents.
Okay, so less land area sticking way up high, exposed to the atmosphere.
Exactly. Less exposed land area means a smaller surface area for that silicate weathering reaction to actually happen. Less rock physically exposed to rain and atmospheric CO2. Less mechanical erosion creating fresh mineral surfaces to react. So the main tech CO2 removal process was just much less efficient.
And that inefficiency allowed the volcanically sourced CO2 to build up to those incredibly high levels and stay there.
Precisely. It maintained that stable, high-concentration greenhouse buffer for potentially billions of years. This continuous volcanic greenhouse forcing is what prevented widespread, permanent Archean glaciations despite the faint sun. It kept things mostly stable and warm.
But it also created a system that was maybe fundamentally vulnerable. By relying so heavily on just CO2 from volcanoes, it set the stage, perhaps, for when a new biological player, oxygen, eventually arrived and started messing with the atmospheric chemistry in a totally different way.
Exactly. It was stable, but maybe precariously balanced on that volcanic CO2 input and the restricted sinks. Any major change to sources or sinks could have big consequences down the line. And that brings us neatly to the emergence of life, and specifically the life that produces oxygen. We know the biological source, oxygenic photosynthesis, carried out by ancestral cyanobacteria, blue-green algae, basically.
And the evidence suggests this process, life-making oxygen, started really quite early, doesn't it? Some of the sources argue for interpretations of microfossils or stromatolites, these layered microbial mat structures, suggesting cyanobacteria might have been around producing oxygen as early as 3.5 billion years ago.
That's right. Maybe even earlier, the date's debated, but certainly by the mid-Archean, the biological engine for oxygen production seems to have been in place.
Okay, so if life was pumping out O2, possibly by 3.5 game, why did the atmosphere only really start accumulating significant oxygen around, say, 2.4 to 2.5 billion years ago? That's a billion years, maybe more, a billion-year delay. That's the absolute core puzzle of the GOE, isn't it? Why the... Wait.
It is the central question, and the answer lies almost entirely on the other side of the equation, the sinks. The Archean Earth had an absolutely overwhelming geological and chemical appetite for oxygen. It was essentially a colossal chemical sponge.
Consuming planet.
That's a great way to put it. This period, before oxygen could build up, represents stage 1 of Earth's redox evolution, as the sources call it. The planet was just so chemically reduced, meaning it contained vast reservoirs of stuff that readily reacts with oxygen, stuff like dissolved iron, methane, volcanic gases, that any little puff of O2 produced by those early cyanobacteria was instantly gobbled up. It reacted immediately before it could escape the local environment, let alone build up in the ocean or atmosphere.
Okay, let's break down the scale of these sinks. What were the main culprits? Starting with the biggest one, probably? The oceanic sink?
Yeah, the oceans were the first line of defense against oxygen. The deep ocean, especially, was completely anoxic, no free oxygen, and it was saturated with dissolved ferrous iron, F2 plus puffsclep. This dissolved iron acted as an incredibly effective, instantaneous oxygen trap.
How did that work?
Well, cyanobacteria lived mostly in the shallow, sunlit surface waters, producing O2 there. As soon as some of that O2 diffused downwards or mixed into the deeper water column, it immediately reacted with the abundant dissolved Fe2+. Oxygen oxidized the iron from ferrous, Fe2+, to ferric, Fe+. And ferric iron is basically insoluble in water. It forms iron oxides, essentially rust.
And that rust just precipitated out, sank to the bottom.
Exactly. It rained down onto the seafloor, forming these very distinctive sedimentary rocks that are one of the most visible signs of this whole Archean process. The banded iron formations.
BFs.
The BIFs, they're incredible looking. These layers of red iron oxide alternating with gray silica or chert.
They really are visually stunning. They represent this massive geological archive. They record the operation of this huge oceanic iron sink, consuming basically every scrap of oxygen produced for hundreds of millions, maybe even billions of years. The fact that large BIFs continue to be deposited right up until the late Archean, just before the GOE, confirms the deep ocean remained a major anoxic reservoir full of that reactive iron. Okay, so the ocean sink was huge. What about sink number 2? The atmospheric sink. We already established the Archean atmosphere was full of CO2, but also other gases that could react with oxygen.
Yes. And the most critical atmospheric sink was probably methane, CH4. Methane was likely quite abundant, produced by early life forms called methanogens microbes that make methane in anoxic conditions. And methane was actually really important, potentially, for helping solve the faint young sun paradox, because it's a much, much more potent greenhouse gas than CO2, even at lower concentrations.
A methane haze could have added extra warming.
Could have, yeah. But the downside, from oxygen's perspective, is that methane is highly reactive with free O2. So any oxygen molecule that managed to leak out of the ocean and into the atmosphere would very quickly encounter a methane molecule and react with it, oxidizing the methane to CO2 and water. This oxidation of atmospheric methane was a major destructive pathway for oxygen, keeping its atmospheric concentration vanishingly low.
Okay, ocean sink, atmospheric sink, and then there's the planet itself constantly burping out, reducing gases. The geochemical sink.
Right, the planet's own metabolism, if you like.
Yeah.
Continuous volcanism and hydrothermal activity were releasing gases straight from the mantle and crust. Gases like hydrogen sulfide, H2S, carbon monoxide, CO, maybe free hydrogen, H2. These are all reduced gases. They readily react with and consume oxygen. So you had this constant flux of reducing volcanic and metamorphic gases, essentially scavenging any free oxygen that might momentarily appear at the surface.
It really paints a picture of a planetary-scale immune system fighting against oxygen. Life is trying to produce it. But the oceans, the atmosphere, the rocks, they're all conspiring to destroy it instantly.
That's a good analogy. The atmosphere stayed stubbornly anoxic, or at best weakly reducing, because the planet's geological and chemical reservoirs acted like this giant proactive sponge. It was soaking up oxygen much, much faster than biology could generate it.
So the GOE, the Great Oxidation Event, couldn't happen until that sponge was finally full, until the sinks were overwhelmed.
Pretty much. Or, more accurately, until the capacity of the sinks was significantly reduced. That saturation, or reduction in sink capacity, required a fundamental shift in the way the planet itself operated. Life was ready and waiting, but the planet's basic metabolism had to change first.
Okay, so this brings us right to that critical transition. Stage 2 of the GOE, the period roughly from, say, 2.46 billion years ago down to maybe 2.06 G. And the key idea here is that this wasn't just a slow, gradual increase. It was a tipping point. A threshold was crossed. And that required, as you said, both the biological source may be increasing or becoming more efficient, A and D.
Yeah.
Crucially, those massive geological and atmospheric sinks declining substantially almost at the same time.
Exactly. It's a synergistic relationship. You likely needed both sides of the equation to change. Less consumption, maybe more production or more widespread production. And this is where the tectonic prerequisite really comes into focus. This is where geology arguably takes the lead role. The key seems to be the maturation, or maybe intensification, of crustal formation and recycling processes in the late Archean, particularly the significant increase in the generation of stable continental crust, roughly between 2.7 and 2.4 billion years ago. There were major pulses of crust formation then.
Okay, but why is making more continents or recycling crust more efficiently so critical for changing the chemistry of the atmosphere, potentially hundreds of millions of years later? What's the connection?
The connection is all about permanent sink removal, specifically the removal of reduced carbon, organic matter. As life produces oxygen through photosynthesis, CO2 plus H2O, when it's CH2O plus O2, it also produces organic carbon, represented as CH2O. If that organic carbon just decays or gets respired quickly, it consumes oxygen again, and there's no net change.
Right, the cycle just closes.
But if you can take that organic carbon and bury it somewhere it can't react with oxygen, somewhere it's removed from the surface system for a very long time, then the oxygen it was produced with is left behind. And that's what more efficient, deeper tectonic recycling seems to have provided, a mechanism for the deep, long-term sequestration or burial of that reduced organic carbon.
So how does that work physically? The organic matter gets buried in sediments?
Exactly. Organic matter produced by life, mostly microbes, gets buried in muds and sands on the seafloor or in basins. If those sediments then get caught up in tectonic processes like subduction or deep burial during mountain building, that carbon gets taken down deep into the crust, maybe even into the mantle.
And down there, it's locked away.
Locked away from the surface oxygen. It might get metamorphosed into graphite or potentially even incorporated into minerals like diamond if it goes deep enough. The key is it's removed from the surface exchange system. It can't easily react with oxygen anymore. And this permanent burial of reduced carbon means that for every atom of carbon you sequester deep down, you leave behind a molecule of O2 at the surface that doesn't get consumed.
Ah, okay. So the efficiency of burying the waste product, carbon, determines how much of the desired product oxygen can build up. And maturing plate tectonics, or something plate-like, was the key to efficient burial.
That appears to be the critical geological breakthrough. By physically reducing the rate at which buried carbon was recycled back to the surface to be oxidized, the maturing tectonic system lowered the overall chemical sink capacity of the planet. The geological sponge was finally becoming less absorbent, you could say, making the atmosphere vulnerable to that continuous O2 drip from cyanobacteria.
Geology provided the precondition.
Okay.
Once that deep carbon sink started working better, did that trigger other feedbacks? You mentioned the atmospheric methane sink declining too.
Yes, once oxygen started to gain even a tiny foothold, maybe in surface waters, it likely triggered a powerful feedback loop involving methane. Remember, methane was a big oxygen sink, and it was produced by methanogens that hate oxygen. As soon as O2 levels rose even slightly in surface environments, it would have become toxic to many methanogens, reducing methane production.
Yeah, less methane being made.
And at the same time, even a little bit of oxygen allows other microbes to thrive. Aerobic methanotrophs. These are bacteria that actually eat methane using oxygen to do it, so you get a double whammy. Less methane being produced and more methane being consumed by these new oxygen-using microbes.
Which would dramatically slash the amount of methane escaping to the atmosphere to consume any free oxygen there.
Exactly. It would cause the atmospheric methane sink to decline sharply. So, picture this. The massive ocean iron sink is finally getting saturated or overwhelmed. The deep carbon burial sink is improving thanks to tectonics. And now the atmospheric methane sink starts to collapse due to these biological feedbacks. Suddenly, the O2 molecule has a fighting chance. It can escape the ocean, survive longer in the atmosphere, and actually start to accumulate. That's the tipping point.
The switch flips. Now we need the definitive proof. The smoking gun geological marker that tells us precisely when the atmosphere went from fundamentally reducing to having at least some persistent oxygen. And the sources point squarely at the sulfur isotope record.
This is probably the most elegant piece of geochemical evidence we have for the GOE. If you look at sulfur isotopes preserved in sedimentary rocks like shales and pyrites before the GOE, so in the Archean, you find this really weird, unique signature known as SMEF. That stands for sulfur mass-independent fractionation.
Okay, mass-independent. That sounds counterintuitive. Usually chemical processes fractionate isotopes based on their mass difference, right?
Yeah.
Heavier isotopes react slower, lighter ones faster.
Normally, yes. That's mass-dependent fractionation, MDF. It follows predictable rules based purely on the mass difference between isotopes like sulfur-32, 33, 34, and 36. MIF, mass-independent fractionation, means the isotopes are being separated in proportions that don't scale with their mass differences. Something other than just mass is driving the separation.
And for sulfur, what causes this weird mass-independent effect?
It's specifically linked to photochemical reactions, reactions driven by light involving sulfur dioxide, SO2, gas high up in the atmosphere, specifically the photolysis, or breakdown of SO2 by very high-energy, deep ultraviolet UV radiation, light with wavelength shorter than about 200 nanometers.
Deep UV. Why is that specific wavelength important?
Because those specific UV wavelengths interact with the different sulfur isotopes in SO2 in ways that depend on factors other than just mass, like molecular symmetry and excited states, it leads to this non-mass dependent sorting of isotopes into the reaction products. These products, containing the weird S-MIF signature, then eventually settle out of the atmosphere, get incorporated into sediments, and preserved in the rock record.
Okay, but why would SO2 in the upper atmosphere only be exposed to that deep UV radiation before the GOE?
Ah, because deep UV radiation is effectively blocked by an ozone layer. Ozone, O3, is formed from oxygen, O2, in the stratosphere. If you have essentially no O2 in your atmosphere, you have no ozone layer. Without an ozone layer, that harsh, deep UV sunlight penetrates all the way down through the atmosphere.
So the SME signature found in Archean rocks is basically a proxy, a direct chemical fingerprint of an atmosphere lacking any significant oxygen and therefore lacking an ozone shield.
Precisely. It's the smoking gun for a deeply anoxic atmosphere. And the truly crucial observation is the permanent global disappearance of this S-MIF signal from the rock record right around 2.46 billion years ago. It just vanishes. Forever. That cessation marks the precise moment that atmospheric oxygen crossed a critical threshold concentration enough to start forming at least a rudimentary ozone layer that could block out that deep UV. It's the timestamp for the irreversible shift.
Wow. And how much oxygen did it actually take? How much O2 was needed to build that initial ozone shield and shut down the SMIF signature? Was it anywhere near modern levels?
Not even close. That's one of the most surprising aspects. The modeling suggests the atmosphere only needed to reach an oxygen partial pressure of about 10 to 5 of the present atmospheric level.
10 to the minus 5, that's 1 part in 100,000. Tiny.
Incredibly tiny, yes, but that minuscule amount, maybe just 0.001% of today's level, was apparently enough. Enough to absorb the critical deep UV wavelengths, form enough O3 to provide shielding, and permanently switch off the SMEF production mechanism worldwide.
So the GOE wasn't initially about breathing room levels of oxygen. It was about crossing this incredibly low but fundamentally game-changing atmospheric chemistry threshold.
It was absolutely a threshold crossing, not arrival at the destination. Once that threshold was crossed, oxygen levels did rise further, maybe reaching a few percent of modern levels during stage 2 of the GOE. But as the sources emphasize, it wasn't instant stability. Stage 2 was followed by stage 3, often called the boring billion, where oxygen levels might have actually dipped again or stayed relatively low and fluctuated. It shows the planetary reservoirs, the oceans, the crust were still adjusting, still absorbing and cycling this new reactive gas for hundreds of millions of years before the really high oxygen levels needed for animals arose much, much later.
Okay, so the SMIF signal disappears, oxygen crosses that tiny threshold, the ozone layer starts to form. But the most immediate, and arguably most traumatic consequence, wasn't about new life forms appearing, it was about the climate going into a deep freeze. The price of oxygen seems to have been the Huronian Glaciation.
Yes, the timing is just too coincidental to ignore. Right after the evidence for the GOE kicks in, around 2.4 to 2.5 gauge, we see geological evidence for arguably the most severe and prolonged ice age in Earth's entire history. The Huronian Glaciation, or maybe a series of glaciations lasting intermittently for maybe 200 or 300 million years, from roughly 2.45 down to 2.2 billion years ago. We find these characteristic glacial deposits, diamictites, basically jumbled rock debris dropped by glaciers on virtually every continent, suggesting ice sheets were incredibly widespread, possibly even global snowball Earth events.
A planet covered in ice. And the cause seems directly linked to the very gas that had just started to accumulate, oxygen, and its effect on methane.
Absolutely. The catastrophic mechanism comes right back to methane, CH4. Remember, methane was likely a crucial greenhouse gas helping keep the Archean Earth warm under the faint young sun. It's much more potent than CO2. As soon as oxygen crossed that critical 10 to 5 PAL threshold, it would have started rapidly oxidizing the atmospheric methane it encountered. O2 plus CH4 yields CO2 and water.
And we need to really underline the difference in greenhouse potency here. Why was swapping methane for CO2 so catastrophic for the climate?
Because, molecule for molecule, methane traps far more heat. Depending on the timescale you look at, its global warming potential is maybe 30 times, or even up to 80 times, greater than CO2 in the short term. So when oxygen essentially scrubbed the atmosphere of its potent methane blanket, replacing it with much weaker CO2, the planet suddenly lost a huge chunk of its thermal insulation.
Like ripping off a thick duvet and replacing it with a thin sheet on a cold night.
Exactly. The removal of that methane shield, which had been perhaps the cornerstone of Archean climate stability for a billion years, caused global temperatures to plummet, just crash, plunging the planet into this deep, prolonged icehouse state, the Huronian glaciations.
It brutally exposed how fragile that Archean climate system was, being so reliant on this biologically produced gas, methane, that was just waiting to be oxidized.
It really did. The shift from a methane-influenced greenhouse to an oxygen-present atmosphere seems to have forced the climate into profound instability.
And on the biological side, for the life that existed back then, mostly anaerobic microbes, this new oxygen wasn't just changing the climate, it was directly toxic.
Oh, absolutely. It would have been a profound crisis, often called the oxygen catastrophe or oxygen crisis, from the perspective of existing life. Free oxygen is highly reactive and damaging to cellular components if you don't have metabolic defenses against it. For obligate anaerobes, microbes that literally cannot tolerate oxygen, it was lethal. So you likely had mass die-offs. Vast populations of anaerobic microbial mats would have been poisoned, stressed, wiped out. Especially when combined with the extreme cold of the glaciations, it fundamentally reset the biosphere.
A catastrophe for the incumbents.
Mm-hmm.
But like many crises, it also created an enormous evolutionary opportunity, didn't it?
The greatest opportunity the planet had seen, arguably. Because oxygen, while toxic, is also an incredibly powerful fuel for metabolism if you can learn to harness it. Its high redox potential, its ability to accept electrons, makes it the perfect partner for extracting energy from organic matter. So the survivors, the lineages that developed defenses against oxygen toxicity and then learned to use it for respiration, they hit an energetic jackpot.
Aerobic respiration, using oxygen to breathe.
Exactly. It yields vastly more energy, like 15 or 20 times more ATP per glucose molecule compared to anaerobic pathways. This huge energetic leap, driven by the availability of oxygen, was almost certainly a key prerequisite for the later evolution of larger, more complex cells, the eukaryotes. And eventually, for things like mitochondria, the powerhouses of our own cells, which likely originated from an oxygen-respiring bacterium being engulfed.
So the crisis drove the innovation that enabled all complex life that followed.
It seems that way. And finally, the GOE wasn't just a surface and atmospheric event. The sources suggest its effects permeated right down into the deep Earth, connecting the atmosphere back to the mantle cycles.
How did oxygenation at the surface change things deep down?
Because the material being subducted changed. Once the surface environment, the oceans and sediments became more oxidized, that oxidized material, things like sulfates instead of sulfides, ferric iron minerals started getting carried down into the mantle via subduction. This changed the chemical composition, the redox state, of the mantle source regions where magmas are generated, and we see evidence for this. Geochemists start finding signatures of more oxidized magmas, sometimes enriched in sulfur derived from subducted surface materials, appearing in the geological record around subduction zones after the GOE. It tells us the oxygenation wasn't just skin deep, it was integrated into the whole planet's convective system. A permanent whole planet transformation, driven initially by tectonics maturing, realized by biology's innovation, and then cemented by global chemistry flipping. #outro.
Wow. Okay, this deep dive, it just fundamentally reinforces how nonlinear and deeply interconnected Earth's evolution really is. We started with that almost shocking speed of the Hedian setup. Liquid water, the basic crust mantle split, a thick atmosphere, all seemingly in place by 4.4 billion years ago. Just boom.
Yeah, and then you contrast that incredible initial speed with the almost agonizingly slow billion-year delay before oxygen could actually take hold in the atmosphere. The planet was, in a way, chemically armed against its own inhabitants' waste product for over a billion years. It had to sort of exhaust its natural geological capacity to consume oxygen before life could finally gain control of atmospheric chemistry.
So if we had to boil this down, synthesize this huge amount of information for you, the listener, maybe the core takeaway is this. The Great Oxidation Event, the rise of oxygen, it was less about when life started making it and far more about when the planet finally stopped consuming it so efficiently.
I think that's a really good way to put it, yes. The critical prerequisite wasn't just the evolution of photosynthesis. It was the maturation of those deep Earth geological processes in the late Archean. Specifically, that more efficient crustal recycling and the deep burial of organic carbon. Tectonics effectively changed the planet's metabolism first. That geological shift allowed the old methane-influenced atmosphere to eventually fail, paving the way for oxygen to build up and enable a completely different, though initially toxic, form of planetary habitability.
Which leaves us with a final, maybe slightly provocative thought for you to mull over. Think about it. The entire Archean climate system, the one that successfully kept Earth warm and wet under a faint young sun, relied heavily on methane, a potent but easily oxidized greenhouse gas, largely biologically mediated. When oxygen finally arrived on the scene, that previously stable, warm system failed spectacularly, plunging the planet into the deep freeze of the Huronian ice ages.
So was that catastrophic climate instability a necessary evil, an unavoidable step on the path to complexity? If a planet's early climate stability depends on a volatile, easily oxidized gas like methane, does that imply that achieving stable long-term habitability suitable for complex life requires that initial, fragile system to eventually fail, to crash and burn, essentially clearing the path for a more metabolically powerful but initially hazardous gas like oxygen to take over and become the engine for everything that followed?
An immense planetary gamble, a risk that ultimately became our greatest reward. Thank you for joining us for this deep dive. We'll see you next time.